Good morning. Good afternoon, actually, for you, I think for most of you. Can you hear me?
Yes, we can hear you, teacher.
That's perfect. I'm glad to hear. So I hope you are all inside of this lecture. Let me see how many people. Quite a few, actually. Okay, I will let some time for everyone to started attending this meeting. You consent to be included? Yes, of course. Yeah, please feel free to to download the today's, which is not really a presentation, is sort of more of a workshop. So unfortunately, we will not have time to really follow you as in a real workshop, but it's not either a pure presentation. So we will be doing things together. I will be doing things, and you will be able to follow along. Of course, you might not have all the software installed. I didn't ask this because some of you may not have the background. I don't know your background one by one, but feel free to stop me in case you don't understand something. But of course, you will also have the recording so that you can use it later on. A small introduction. Today, we will be dealing theoretically with, you read, with the traditional Chinese villages, but actually, we will be using some data which I have more, at my disposal, which is, I will show you how to use what we will be learning here also for Chinese villages, but actually the data we will be using will be taken especially for my city, Milan, because I've been working on those data sets. I have much more materials, and it works, and I think it's a good example. But nevertheless, I will show you how to use the techniques we are discussing today for any kind of built environment. Another couple of premises. Today, we will not be dealing with the most cutting edge advanced artificial intelligence models, because that would require expertise that even myself, I don't have that expertise. I'm not a software engineer. I'm a lawyer and architect. I do research in this field, but of course, we use models which are mostly created by software engineers. Nevertheless, it's important, in my opinion. You will see why, to become accustomed to these tools, because these tools are really powerful and promising for our own profession. Moreover, today we will also show something, an entire workflow, which will add different software packages along the the reasoning. Why? Because very often nowadays we need to really create workflows, and there it lies the value of our research. Research these days is not only using ready-made packages, rather connect them in a way that we make sense of those tools in order to achieve something that is interesting to our own research. Okay, I've been talking a little bit so that all the people who might be late could enter. Again, please feel free to stop me, interrupt me if you don't understand. If you don't understand my pronunciation, I am an Italian with a thick Italian accent, I think. So if you feel free to tell me we didn't understand this word, we didn't understand what you said, or we are not familiar at all with this concept, I will try to wrap up in a faster way. Having said this, we will now start. There will be three main parts of this lecture workshop. The first part will be dealing with getting data. Why? Because, of course, when we deal with the built environment, we are not dealing with fantasy world. We are dealing with real data. So, as you may know, real data we can get ourselves using drones, using photogrammetry, using more advanced techniques, starting from surveys. But today we will not be dealing with this. Today, in order to get a faster, more universal, so to say, starting point, we will be using data which were already collected and which are available for free throughout the world. In particular, we will be using GIS data from OpenStreetMap. This is a nice hybrid system because OpenStreetMap is something you can contribute to, a bit like Wikipedia or some other of this kind of online platforms where users can actually enhance and add detail, add data. So if you happen to do a survey and have personal data, you can actually contribute to OpenStreetMaps, and then use those data also using the workflow we are looking at today. The second part will be based on those data to yeah, I see a question.
Hi, sorry, teacher, for the interruption, but we can't see the screen share of your computer.
Sorry. I haven't shared the screen yet because there is nothing to be seen at the moment, but I will now share in any case my screen. Can you see my desktop?
Yeah, we can see.
That's perfect. Okay, so the first part will be based, the data gathering part will be based on QGIS. So if any of you already has QGIS installed, please, open it or install it. In any case, this will be the software we will be using. This is an open source, free of use software, which is quite good. The second part will be based on Rhino Grasshopper. As you can see here, there will be a very short definition, which I created for normalizing data. Basically, what it does is it gets the data, in this case, it would get the shapes of the kind of buildings we will be trying to train the artificial intelligence model on, and normalize their positioning and size so that the model can actually work with those data and not be confused by some differences, such as the position or the scale, which could alter significantly the outcome. So it's very, very important that data are not just taken as they are, rather they must be quite always, I would say, data must be somehow selected, normalized, and also curated. You cannot usually just take, like scrape data from the internet and purely use them as they are, because otherwise the model would be highly unreliable. Last but not the least, we will have a final software. Here, the software is called Quasar, but actually this is just a more complete version of Orange data mining. I will write it somewhere, but in any case, also Quasar is a very nice package. This is a little bit like those intelligence routines written in Python. But luckily for people who are not good at coding, you can use the components in order to create a work pleasant and clear. At least to me, this is much easier to understand, and somehow it's very modular. So in a way, I think it's easier not to make too many mistakes. Of course, this is also open source tool created by University of Ljubljana, if I'm not mistaken, and it will be the way we train our own model, and also will test and try to see the potential and also the shortcomings of the models, the artificial intelligence models, for the assessment of the built environment. Is it all clear now, the starting point? This is good. So let's start from are some plugins. If we go to plugins, I will, teach you today as if you could really follow along. I'm not sure you have the capability. Sure you have or all. Never that so that you can follow what I'm doing. In any case, the QGIS has the possibility of plugins. You see, manage and install plugins, and I hope you can see all the windows coming up. You have the installed and non-installed plugins, so all plugins. In any case, I type OSM, which is OpenStreetMap. And as you can see, there are many plugins. I have some of them already installed, including the Quick OSM. If you don't have it installed, you can install or the plugin. I think now because it's already installed. What it does connect QGIS to the online database of OSM. I go here, Quick OSM, I click on the icon, and here we can retrieve GIS data from the internet. You have the whole world at your disposal. The important thing to know for people who are not familiar with GIS, but might be familiar with BIM, so Building Information Modeling, GIS is a similar tool for the built environment, for cities, for towns, because every element is not just a geometry, it is a geometry with a set of information. It's a database which is including geometries, but also other kind of data. And this data you can see quite easily. The key is somehow what in the BIM environment would be the industry foundation class. In this case, the categories are a little different. For instance, we have buildings. I type building, and you see one of the categories here is building. In the value, you can see in the drop-down menu, you may have garage, hangar, hotel, house, industrial, mosque, retail, synagogue, temple, and so on and so forth. So let's say we want to see, I don't know, let's see now, it could be anything, okay? It could be really anything. Let's do farm. Let's see whether we get any farm. Then there is the in. In is basically, in this case, referring to a real geographic location using a label, which is quite useful, I would say. In this case, you could suggest me a nice agricultural land in China, but maybe I'm not good at writing it down because of the different alphabet. Town. What I can use here is actually something like an Italian place. I could, for instance, say Pavia, Italy. Pavia is actually a town, and it might have some farms. I'm not sure, actually. Let's say this is my choice. So within the key, which is building, and the value, and everything which is a farm building within this area of Pavia, Italy. But of course, you can also decide the extent of the layer you already have. I mean, there are many options. I just run the query. Okay. Apparently successful query, 2 layers. We see in the, okay, this was open from me before, so you have a lot of layers in QGIS, but what is important now is that we have these 2 layers. You see the building from Pavia, Italy. I can click, right click on this, zoom to layer, and you see that if you zoom in, actually quite a few shapes which are georeferenced. So you see they are in. of Pavia. You cannot see the city because at the moment I only downloaded the these elements. But it's important because now we will perform morphotypological analysis of these kind of shapes. Of course, in this case, the shapes are pretty banal. They're mostly all rectangles, which is not particularly interesting. But this is not the case for all of the buildings. For instance, I did the same thing before with the church in Milan. Let's zoom to layer. Yes, please. Hello. Hello. Any questions? In any case, as to the farms we saw around Pavia. So the same thing may apply to Chinese architecture, especially vernacular architecture, in different places and in different ages. As you can see, the churches in Milan are, have some basic typologies. This is a typical basilica typology, and some others are a bit more complex. These are the Latin cross. We may also have a Greek cross. We may have a more as of a Pantheon kind of style. So we can, immediately recognize there are quite a few different archetypes, which are, morphotypological elements stemming from the plans of these elements. Of course, these are simplified plans, which you can directly retrieve from OpenStreetMap. Once you have these elements, you choose, let's say now, let's do the churches in Milan, but we can do with the buildings from Pavia or any other things I tried before. So I right click here, I let me export, save features as, and I decide to export the geo package. Geo package means that you export all this layer, which encompasses not only the shapes, but also the georeferencing of those shapes, and also all the, the semantic aspects, so the categories, everything which pertains to those shapes. So not only shapes, but shapes with all the data, all the GIS data relating to those shapes. Then file name, you go here and you save the data in the folder. For instance, churches Milan. I already exported it before just to practice, but let's do it again. Save. Of course, it should ask me whether to overwrite. Of course, I want to overwrite the file. It can overwrite. In any case, we already exported those before, so don't worry. It added a layer to my QGIS, but that doesn't really matter at the moment because we are using QGIS for the sole purpose of exporting those geo packages and be able to gain some create an artificial intelligence model which is able to then recognize some pattern, some morphotypological features. Is it clear until now? Maybe let's do another example so that you have time to follow along, but also to raise some questions. If you type, you see A, you see or B, you see that there are there's a drop-down menu which is actually telling you what kind of categories are in the database. This is important if you're not particularly how can I say, particularly used to using these tools. You can actually get some kind of inspiration. For instance, another example we will be using is amenity. Amenity, you go on the values, and the values are, for instance, bank, bar, barbecue, art center, bicycle rental, brothel, even cafe. You have so many things. Why are we here? Because we used the hospitals. So where are hospitals? Hospital. So the example we did, I speak in plural because this was actually used by a colleague of mine, Matteo Cavaglia, who kindly gave me advanced, how can I say, improved data sets we actually got from this software. So in that case, it was the hospital in Milan, but we can also do, for instance, hospital in Xi'an. Let's run the query. Okay, I turn off the churches in Milan, which are not interesting anymore. Let's right-click on the new layer, zoom to layer, and these are all the hospitals in Xi'an. As you can see now, the shapes are quite different. Of course, hospitals tends to be a bit more blocky. But this could be interesting if we wanted to compare the morphotypological aspects of a hospital in Xi'an or in any other place. Now let's right-click on the amenity hospital, export the layer, save features as the file name could be hospitals, and I hope the name doesn't impact the file system. Save. Add save file to map, yes, why not? And as you see now, there is an added layer, which are the hospitals as they have been exported. Questions so far? Okay, so either no questions. Now we will move to the next stage of this research. The next stage is, one question, please. Kibir Kolani.
Oh, hello, Professor. Sorry, there is a question in the comment section.
Sorry, where in the?
In the comment section, the conversation.
Can you please maybe speak out, because it's easier for me to see and to answer. But now I will try to go to the comment section, which I don't see, by the way. Can you please maybe read it out loud? Because as you see, I'm really struggling to see where this.
Okay.
Yeah.
The question is it possible to do the same thing using ArcMap? ArcMap.
It's possible to do the same thing using anything. The point now is just to get images. Today's workflow is a very, how can I say, easy, down-to-earth system based on image recognition. So it does not use 3D data, it needs images. So the way you get images is up to you. You can get images also from your own survey. You can use a script. I created a script in Python, which is super easy. You know, you just create an area and you type what you want to see and what you want to get, and it's super easy to do. So you absolutely don't need this. This is sort of easy for trained architects because usually you know how to use QGIS. So I wanted to start from something easy, but it's absolutely up to you. You can use whatever. You can also use some very nice plugins in Rhino, Grasshopper. I didn't want to overload you with those kind of things, which are maybe a bit more complex. This is, I would say, the easiest way, but it's up to you. By the way, it's not necessary that you use OpenStreetMap data. You can use other kind of data. You can use private data sets. You can use whatever else data set. The important point here is just getting some kind of data which are comparable. Because of course, if you get some plans which are super detailed, some others which are completely rough, some are taken from different sources and not easily comparable. Then in that case, the software, the model, the artificial intelligence would struggle to compare them because we would struggle ourselves, right? As we see, we usually don't compare oranges to apples. So it's better that we have one source, or at least sources which are really compatible.
All right. Thank you, Professor.
Thank you. Any other question? Okay, good. So the next step is entering in Rhino. I already am in Rhino 8, Rhinoceros, it's a McNeil software. But by the way, if you don't know it, it's a very powerful nerves modeler and also software in which you have 90 days free trial. And so in case you don't have it, you may try it. It's a very powerful tool because it has also an embedded plugin, so to say. So the embedded plugin is called Grasshopper. You can study from here, let's pretend it's not open already. We are in Rhino. We can have new model, for instance, new large object meters. It could be. Okay, it doesn't really matter because what we are now using this software for is just creating the images from those geo packages we exported. We now need to create the images. So let's open Grasshopper. We go here. I tell you already, in Grasshopper, you will need some plugins. I already, of course, installed all of those plugins. I will nevertheless tell you which plugins will be needed in order to follow along, but this could be something you can do in a second moment. The important thing is that you follow the concept. So the main plugin that you need here is Heron, which is, this plugin here. We are now within the Grasshopper canvas, which is the interface. Grasshopper is a visual programming language. So again, these components are basically like scripting one or more lines of code, but you don't need to code. You can just create this workflow in a very visual way and obtain something which is equivalent to coding. Okay, for some specific purposes, it would be very, very hard to do with a standard Grasshopper. So as you can see up here, I have quite a few plugins installed. To install the plugins, you go to File, Special Folders, Component Folders. Then the component folder should appear. Now it's taking time, maybe because it was already open. Yeah, it is this one. So is the libraries. And then when you want to download any kind of plugin, you just go to Food for Rhino. I tell for people who already don't know, Food for Rhino. Food for Rhino. And then here you can choose. For instance, if you need GIS materials, I mean, components which are dealing with GIS tools, you can find quite a few. For instance, at IT, which is quite good, to be honest. And the other one is Heron. Heron is the one we will be using today. You open the page, you see there are different versions. There are even some examples. And you download. Okay, this is in Italian, scarica, which is download. You download this, and then you save the file in this directory, which I showed you before, like the libraries. When you download something, make sure that you go to properties and it's not blocked. Sometimes it's blocked because you have been downloading from an external source, and then for security reasons is not unblocked by default. So unblock it if it's blocked. Okay. This way you usually install plugins. Some of them are actually installed through an exe file or something similar, but it doesn't matter now. Let's do the easiest case. In any case, the Heron is here. You see, it's a folder with inside has a lot of components and DLLs and that's it. Then you restart Rhino Grasshopper, and you will find your all your different plugins here. Okay, what is this plugin for? What are we starting to do? We downloaded, as you may remember, a geo package file. So the first thing we need to do is to reference that information within the Grasshopper interface. So we double click, right click on the canvas and type file path, and you see that the component file path will appear. We right click on file, and as you can see, you can select one existing file. So I go here, and of course now the default is not the folder I want. So I need to go to the folder I want, which is a little complicated here. It's here, and it's here, and then it's here, and then it's here. Now, we have many geo packages I downloaded before, as an example. For instance, Churches Milan, or we have Farms Pavia. I even did Golf Clubhouses China, Hospital Xi'an. Let's do the Hospital Xi'an because we did it together right now. So I click on this. Okay. The other file path was actually already attributed to maybe Farms Pavia, but I want to do the hospitals because that's the example we will be doing. Okay, so now we have two file paths. The first one is related to the hospitals in Milan. The second one is the hospitals in Xi'an. Good. So let's connect the file path to this component, which is import vector light. You can find it here under the Heron, you see Heron plugin, GIS import export, and one of these components is import vector light. It's an easy way to import the geo package. I connect the file path to file path, And what gets, the output we get, so on the left-hand side, we have the input, on the right-hand side, we have the outputs. Here we have many aspects. The important one is, of course, geometry. There are 97 locally defined values. These are 97 geometries. As you may see, if for people who knows Grasshopper, the elements are actually grafted, which means that if you put a panel, you will see that those elements are divided into different branches of a tree. But if we flatten this output, you see now the tree is only one, this kind of zero, is only like one folder. While originally, if you don't flatten, it's like you have many folders. There's 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, and so on and so forth. So this matters. We will see why. It matters because it's something I cannot teach you now in depth, but it's something you should consider if you're following along. Pay attention to this flatten or graft, because sometimes you are, doing operations one by one on each of those elements, which are in different, so to say, subfolders, or you want to have them all together in just one big folder, so to say. So you flatten and you see it's not really actually a folder, it's called a list. But in any case, this is one list. And if you don't flatten, you have actually a series of lists. Okay, so what do we get as, this output is a feature geometry. What we actually get are meshes. We want to refer within this definition to those meshes using a mesh component. We can type on the canvas mesh, and we can connect this. We can flatten the output here, actually. So the mesh now would be, again, in one unique list. I will, let you also do screenshots of this definition, because we cannot go into all the nitty-gritties. But the main issue now is, what are we doing? Why are we doing this? We are doing this for selecting each and every hospital, in this case in Xi'an or in Milan or wherever, any kind of building. And then we need to export them as images. But before doing that, we want to normalize them, so to say. So the current meshes we can bake in the world of Rhino. Just want to show you, select objects, and that's back. You see, these we have baked all these elements within a Rhino in the position, in the original position, georeference position, so very far, potentially very far from the origin of the axis. But this, of course, would not make these images comparable. Besides, the scale is a problem, because we don't want to compare the scale. The scale should not be a factor in deciding the morphotypological aspects. Rather, the shape, just the shape is important. So we need to move all these elements away from where they are and try to get them at the, at the start of the axis. So on the point 000 in the Cartesian world, and also try to get them oriented and scaled in a way that they are comparable, right? Otherwise, this will be completely useless. So I delete this. I go back to my Grasshopper definition, and now I show you what I can do. So first of all, I introduce this list item. List item is a way to see the items one by one. I can move the slider, and it's supposed to be, wait, I rebake. is supposed to be moving along the list, so you can see what element of the list you have been selecting in this moment. For instance, list item, I'm here. If I move, you should see, let's do this, geo. There are too many, it's difficult to see. You are basically selecting the meshes and then selecting which one of those meshes to show. In this case, they are all already baked and they are so spread around that it's difficult for me to make them clear to see. If we are lucky, you will see it, but we are not. Yeah, you see. Can you see? It's very difficult. Okay, now you see one. Now see another one. Of course, by moving by one, you are moving in the, you see, you have this list of meshes and you're moving between one and the other. So what this list item component is doing is getting one by one. You see now it's a clear, is a clear plan of one of the hospitals, and it's number 12. This is the hospital number 12. Then we can create a bounding rectangle. So the component is bounding rectangle. Based on this, we can get the centroid, so the center of such rectangle. And then we want actually to move the whole thing to the start of the axis. The start of the axis is actually a point here, which is called is 0, 0, 0. So the coordinates here are 0, 0, 0. The component is construct point, and we create a point, as you can see, at the beginning of the axis. Now, we can also create a vector between the old center, the center of the bounding rectangle we just saw before. You see, and move it. So create a connection between that point and the start of the axis in order to move the geometry to the start of the axis. Now, it should be already the case that we have been moving that element. I cannot zoom too well. Wait a second. Geometry, bake. You don't see it because of scale, okay? So I'm baking in Rhino so that I can now zoom in. And as you can see, the element is right there, centered on the origin of the axis, okay? This vector 2 point was the vector to move from the previous centroid in the center of the square to the new centroid, which is the center of the axis. Is that okay? And now there is another part. It's a part which is a little bit more abstract, so to say. You can please just, even screenshot it and have a look at it. The main point here is to scale each and every element so that they will be all, based on the same scale. This is very important because otherwise the artificial intelligence model will not be able to compare anything, because the scale would be the most important factor, which should not be, right? So in this case, you can just copy this if you want to follow along. But the main point is that you scale by a factor which depends on, on basically on what you had as an input. So you see, this element is now much bigger than it was. But let's move to other elements. You see, they are all now consistently scaled so that they are comparable. Okay, I hope this is clear. If we don't do the scaling, the components would be something like this. Look, this is this component not scaled. As you see, there is a big variance between the different elements. This would completely, alter the results of the artificial intelligence, discriminator. I mean, the model would not understand because these are not comparable. Why? If we scale, you see, this is big, but also the other ones are big in the very same way. So we have normalized these shapes. Is that clear? I hope it is. By the way, this is an extra component, this custom preview, in which you can also change the materials, the colors, and it could be important because what we want to achieve is actually a definition where the, preview off. I want to show you that we can achieve this kind of black and white result. Why do we want black and white? Because this way the model, the artificial intelligence model, will be more, facilitated in recognizing the pattern. So what is the building? The building plan is, fully black. What is not building is just ground. It's fully white. This is a nice way to simplify the task. You see, now we have all these maps, all these plans of the different hospitals, and this has been normalized vis-a-vis, I mean, comparing to the square we see here. This has been normalized using this definition down here. Basically, it's a system which creates a percentage of the square we saw. If it's 1%, I mean, if it's 1, it's 100% of the square. So we can go lower, we can go higher. As you can see, this part of the definition is basically doing this. Okay? So now we have all the shapes one by one inserted in this square. We can also, of course, automatize the whole thing, and then we can get, all the elements together. Now, it doesn't show because I'm not in this visualization method. As you can see now, these are many, I mean, all the elements that I created before, all on the same place, and we can then export them all together. But let's say we do it one by one, like in this very didactic example. Once we had this, we may use very different methods to export them. We can bake them and create a view capture to file, for instance. So we could bake those two elements. And just go to a top view and then create, view capture to file. We select which view, the top view. We select if it's transparent background or not. Let's say no, because we want something, something which is possibly white. Maybe before doing this, we do the render view, which is really white. And now we do again view capture to file. And we can now, export this element in a picture. There are many different ways to do this. The important thing is that we come out with images. This is just one example. There are many ways. There are also plugins for Grasshopper itself, which are, for instance, a human or wombat, which are all able to export the images directly. But what matters is actually we are exporting. Again, I show you the easiest one, the view capture to file. We are exporting this. Okay, this with also the square, so that we can then cut and have the images all perfectly aligned and all perfectly the same. It's important that we do not include this kind of square in the training data, because this is just for us as a reference. Okay, so you can find your own methods of doing this. The important thing is that at the end of the day, you just export the the plan like this. View capture to file, no transparent background, black and white. This is our output. Of course, you need to make sure that you are maintaining the dimensions, so you don't zoom differently. You need to maintain one specific zoom, and since we have already created the right, scaling, you see, by changing this and baking this one after the other, we can export exactly the same dimension. Is that clear? Questions I don't see maybe in the chat? Okay. If there are no questions, now let's say that we have already created something which looks like this. We have the folder is called classes. It's called classes for a reason. From a technical point of view, these are classes, and then we have the two subclasses, the C and the O. C and O are just simplified, categories of plants. In this case, we want to train a model, and to train a model, we include under the two different folders, all the plans which are, in our own opinion, so somehow it's a supervised way of training the model, the plans which are following a C-shaped kind of plan. In this case, we use these are the images we exported from Grasshopper Rhino. As we saw before, the resolution is not very high, but these are the images. The resolution is not high because with higher resolution, it takes much longer to train. We have the C-shaped plan and the O-shaped ones. As you can see, you see a lot of variation. Of course, the more data you have, the more variation you have, the better it is for training. This actually is probably wrong. I don't know why it was included here. And this could actually bring us to some kind of mistake. So to be honest, I would also, this one is not really correct. In any case, let's leave it like this. But of course, make sure that you check accurately that the data are labeled in a way that you want. The labeling here is done by you by just inserting the right pictures in the right folder. So we have the folder classes, and in those folders, we have the two classes, the C and the O subfolders. These will be very important for the next step with artificial intelligence. Then we see another thing here, classes data augmentation. we have again C and O, but now you see way more examples. As you can see, some of them are exactly the same shape, just rotated. In other cases, the shape is not just rotated, but even created from scratch with artificial intelligence itself in order to have some more artificial data to increase the number of pictures and the variability in the data sets, but still maintaining the fact these are all C-shaped elements. Same goes for the O. In this case, we have much more O-shaped elements, as you can see. And here probably the wrong elements had been already taken away. So this is an augmented data class, class data, and it's an augmented folder with much more images. Again, this is a science, but it's also an art. It's important you provide as many examples as possible, and you classify them very, very carefully, because some of them are actually not so obvious. For instance, these ones don't look super, super obvious. And sometimes it would be nice to have maybe another category, which is like the rest of the world. I don't know. In this case, we have only two categories, the C and the O. And now what do we do with these classes? In this case, classes data augmentation, we will use this because it's, of course, well, we now will use another software. The software is Quasar, or Orange Data Mining. This software is, again, like Grasshopper, is a visual programming language. What does it do? It does a very simple thing. It simplifies the use of artificial intelligence packages based on Python way to use those complex algorithms. Again, also here you can double click on the canvas and you can, for instance, type import images, and you get this component. Now I already have the whole definition up there, but let's do it together. Then if I click on this component, I can choose, where to go and get the images. So the images now is classes data augmentation. Okay, as you can see, it tells me 392 images, 2 categories. The 2 categories are, of course, the 2 subfolders we saw before. Now, we can have a look at what gets imported. There are different ways to, to connect. One would be to double click and write something like image viewer, and then connect. Or you can just, drag and then, keeping clicking, left clicking and dragging. And then you have the suggestion of all the possible components which are suitable after import images. For instance, data table. So image viewer, if we click on this, we see all the images which have been imported, the C's and the O's, all of them, because of course, in this case, it's all the outputs. In the data table, though, we would see that the images are also already categorized in C and O's. Can you see that? This is very important because this will be used by the model to understand what is making something a C or a O. Is that clear? Okay. So we imported the images, we could see the images. We could see that the images also bring some other aspects, size, width, height, name, but also the category, which are the folders. And now we need to do something special. We will now use a pre-trained model, in this case, Inception version 3 by Google, which is a pre-trained model trained again based on images with labels, trained on many billion images with a lot of labels for basically everything. And then based on this pre-classified set of neural networks, we will now compare the imported images to those multidimensional space and try to embed the new pictures within that multidimensional space. This is very difficult. I will try to explain it, but then it's something which is not so obvious. The component is image embedding. So image embedding. We must simply connect the images to image embedding. I'm doing this now. You see that it takes time to work. I did it already up here. We can choose, so what is the image attribute? Image. What is the embedder? We can choose. Inception version 3 is quite good. It's a V3 model trained on ImageNet. And what is the outcome of such an embedding? Well, again, we can use a data table to see the output of this component. So let's make it bigger, because in this case, what has been added are a bunch of, actually very many, almost, they are 2047, 2048 features, so-called features. You can see there are, for each image, the image is, the rows are the images. For each image, we have the so-called features. The features are values which somehow compare the image along dimension. Let's say that in a Cartesian space, we usually have three main dimensions, which are x, y, z. Well, this n1, n0, n1, n2, n3, n4, these are all dimensions like x, y, z. But in this case, we have not only 3 dimensions, we have actually 248 dimensions. What are these dimensions? These dimensions are actually semantic aspects of the image. Unfortunately, this kind of semantics is not some kind of label that humans can understand. These are features that the neural network, the Inception version 3 embedder we are using now, found out itself as relevant to distinguish among different images, okay? So somehow, each of the image here, on each row, we have that values, those values for each of the dimensions, like, like having a point in space, you say x is equal to 3, y is equal to 5, and z is equal to 1. Good. This places your point in a 3D space. In this case, these numbers determine how your point, actually it's a vector, because the important thing is the direction that this image assumes in the multidimensional space in order to compare them. For instance, if 2 images like number 2 and number 3, they have, for instance, very similar, actually equal, they are the same image. This is the same image. You see that every of these elements have the very same numbers. It means that this image is actually the same as the other one. It's like having the same X, Y, and Z. In this case, we have the same 2048 features. So the more these numbers are the same, the more the vectors means are exactly the same, aligned, and have the same direction. These features allow us to compare all the images we had and understand how far from each other those images are. As when we are comparing points and trying to understand, okay, which points are closer to each other? Okay, we do the distance within the XYZ Cartesian space. In this case, we do the distance, but in a much higher dimensional space, which is this semantic vectorial space with 2048 values, feature values. Okay. It's difficult to, this course is just sort of basic, so you will need to maybe try and understand a bit more yourself. But the main point is these features are describing that the image in such a deeper way than just, the Cartesian 3 dimensions, that it's possible using these vectors to compare them in the multidimensional space. Is that clear? Kind of clear? So now we've seen the embeddings, the images have been embedded, and now we can finally train our, use a model. In this case, we use the K nearest neighbor. This is one of the easiest way to compare the different vectors, okay? Based on what? Based on the proximity, the Euclidean distance. So the, the K and N component is this one. We can connect it to the image embeddings. So K and N, great. Sorry, I'm doing again the same script which is up here just to do it with you. So I'm adding K and N, Euclidean, but it could be also other kind of metric. The weight is by distances, and number of neighbors. You can consider different number of neighbors and decide based on the neighbors what is the most likely attribution of your own image to one set of neighbors or another set of neighbors. In your one, how can I say, one group, like the O or the C-shaped plants, right? So the software is getting 7 or maybe 9 neighbors. The more you add them, the more everything changes. And based on this, we can create a model. Basically, we are training a model based on these similarities. Now I increased the number to 9, but 7 was good enough. And now what can we do with K and N? First of all, you can click on this, see, yeah, okay, applied. And then we can do 3 things. One, it would be to save it, but let's keep it for after we check by test and score and confusion matrix. So K and N, test and score, and then also confusion matrix. Test and score, of course, needs to get data from the image embeddings as well as from the model, from this K and N. Okay, if I click on test and score, I get some data like model, AUC, area under curve, and then we have the classification accuracy, and then we have other, specific data. The important thing is that we are these numbers. So a number over 0.9, 0.96 even would be very good. And it's important to see that in this case, apparently the model manages to somehow predict the data. So the model actually subdivides the information into test and in train and test data, and then comes out with a percentage of how you can trust the model. The confusion matrix, in turn, shows it quite clearly. You see, this means on the horizontal is predicted, and the vertical is actual. So the actual O's were predicted, 96.6% of the times as O's. So the mistake was only in a lower case, 3.4% of the cases. As to the C's, the correct predictions, so the diagonal, this darker color diagonal are the correct predictions. So actual C predicted C in 92% of the cases, while sorry, it doesn't. Actual O, but predicted as C is 7.5 of the cases. So we have, we have a better result with the O's, of course, but at the end of the day, it's not such a bad model. Is that clear? So if the model is good enough, we can go here and save model, save as classifier, CNN, blah, 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 save as. I already saved this before, so I don't save it again. And now what do we do? So this is just a duplication of the script we just did. Now we do something different. Now we import images again. So the component is import image. We now import another folder. The folder is test images. Test images contains the images we want to attribute to either O or C plans, right? So these are 6 images. Image viewer shows us which images these are. There is a very questionable case here in the middle. Is this C or O? It's probably neither of them, but we introduced this example as an example of what could be confusing for AI and somewhat what could be misread as either of those or none of those. Then what do we do? Data table, the same. So we have now here these images. The categories are just, something we wrote in the name just to know that they should be C, C, O, O, random. I mean, the wrong one and another C. Good. Now we embed also these images with the very same inception version 3. Why? Because we need to compare these new images based on the very same vectorial space, the very same model. And now, instead of having the model we were training before, the KNN, now we have the prediction. Prediction is using the model, so we need to connect load model, pick the model we saved. In this case, we saved before the, classifier KNN model lecture, which was the one we saved before. So we open the model. We include in the predictions the result of the embeddings. And if we click on these predictions, we get, as you can see, sorry, this is not. Okay. You see KNN, the model we just loaded is the KNN, and we see that for each of the images we have C, C, O, 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 O. Okay, so this is a classification based on the model we just loaded. The images are this one, so let's see whether it's correct. I think it is not correct. So CC, O, O, O. The last one is O here, but actually it should not be O, it should be C, I think. So this is important. Why do we see such mistake? And also the one which is, the random test, the one which is neither O nor C has been considered an O. So here clearly we have a couple of mistakes. One is quite comprehensible, the other one is not. Why this? Because this model, KNN, is not particularly strong, is not particularly advanced, and even the orientation of the image or any other small issue which is not making the images completely comparable to each other tricks the model, and the model cannot really work. So we will see just after I explain you the final part of this definition, other models which could be a little bit more advanced, even though still based on the plain images. So let's read the results better. We connect to predictions the data table. And we see that here we have some more information. We select the columns. The columns I want to select by putting them in the metas are the image, the size, width, the height, the KNN, the KNN-C, and the KNN-O. And now I also connect again a data table which doesn't have all the other columns, which were all the embeddings. And now we can see that the result, the KNN, is the result CC000, but also we have the KNN-C and KNN-O, which are the percentages, so to say. So how much does each of these elements fit that category? As you can see, especially for this C-test2, which is the C which was wrongly put into the O category, we have actually very close numbers. So the model itself wasn't very sure. It wasn't very sure, so that there was kind of 0.42 probabilities that it was a C actually, and only slightly higher 0.57 probabilities it was O. Nevertheless, the final result was wrong, plain wrong. This is to show you that in any case, this machine is maybe wrong, but usually at least is able to show you the level of confidence. When you see 1, 0, it means that it's 100% sure that it's a C. If you see 0, 1, the same thing, it's 100% sure. You can see that the not clear cases come out actually as not very clear to the model itself. What can we do to improve the results? First of all, having a bigger data set with all the possible rotations, permutations, how can I say, the more images you have, the more accurate the prediction would be. But we also can use other models. Instead of using KNN, we can, for instance, use random forest or support vector machine. So I now show you the support vector machine. By the way, pre-process was just a way to standardize. In this case, we standardize to the mean, and we normalize the features. This I skipped before because it's a very technical thing, but it's important because it's again a way to compare data which must be normalized in some way. So this pre-process component, we just use the standardized to mu 0 sigma square 1. It's a complex thing, so just trust me, it's working like this at the moment. However, instead of the KNN, now we will use the SVM, the support vector machine. What is the difference? KNN takes the nearest neighbors, 7, 9, how many neighbors you want, and then tries to see, based on the neighbors, to what kind of neighbors your vector is nearer to, okay? Support vector machine operates in a completely different way. in this multidimensional space, it tries to fit an hyperplane, a barrier, so to say, between one group like the C's and one group like the O-shaped planes, okay? So it tries to find a plane which best describes the separation between the two groups, okay? It takes the very same inputs, like the image embeddings on the one hand and the preprocessor on the other hand. Then again, so let's see, support vector machine. I don't do anything else here. Let's leave it, as it is. It's very complex. It's a completely different method. Even though not super advanced, it's yet a little bit more advanced. Now let's see in test as score and in the confusion matrix. So let's compare the confusion matrix of the previous one with the confusion matrix of this model. As you can see now, the mistakes are much lower because we went from 7.5% of mistake to 3.8 and from 3.4 to 1.1%. So using a different model, having exactly the same data actually improves by quite a significant margin the potential correctness of the model. So let's do something. Just by using this support vector machine instead of KNN, we apparently have a better model. So let's save it. So from support vector machine, we get save model, okay? We go here, we save as support vector machine model lecture. Actually, I already saved that before. We will go down here and load the model. In this case, not anymore the KNN model, rather the support vector machine. Reload. Okay, let's see now if we are lucky, if the recognition, the prediction is actually more correct. These are the images, and these are the predictions. Let me see, because I don't find the images anymore. Images and predictions. Now, as you can see, something has changed. I would say that it changed for the better, because we still have the random test, which is the weird shape, which is neither C nor O and is classified as O. Okay, I can accept that. But luckily enough, the last image is now classified as a C, not anymore as O. So I would say the classification now is correct. This shows that those percentages in the test and score and the confusion matrix are probably correct, at least in this test data. This time we have correct attribution. We can see more in depth in our own data table. And as you can see now, we still have a sort of almost tie in the last image. So now it's attributed to C with a slight margin, yet it's correctly attributed to C. So the table has turned, and somehow we get the right attribution. So this is just to tell you that even based on the same data, we can have different results based on the model we're using. Some models are better for understanding some morphotopological aspects. Some others are probably worse. But the important thing is understanding the workflow. I wanted you to follow along. I'm not sure you could actually follow everything and you will be able to do yourself. But the point here was showing you the potential. Of course, there are much more advanced models which could take different kind of inputs, and it can embed elements which are more complex and result in much more accurate attribution. By the way, this way of working is not just limited to morphotopological aspects, rather also for decay, for instance, or for any other feature which could differentiate between some group of images, some other group of images. This is quite useful, I think, in many fields, and for sure it's useful for the architects and the planners of today, because it can, work on, large amounts of data, and the more data you have, the more accuracy you have. It does not substitute your own, evaluation skills and judgment. Another aspect which is important nowadays in machine learning and artificial intelligence is the so-called human in the loop, because you as a human have the responsibility of checking the model and also to somehow give feedback. As we saw before, it's very important how you classify the data before, how you label the data before, but also, of course, to check how the model works afterwards. So again, there is a margin for training further, to avoid overfitting, to avoid the model being too somehow less robust if you don't have enough data. So it's something that requires some kind of work. But I hope I showed you the potential, and you can be, you can start using these tools, which are, as you can see, free, quite easy to use, and quite powerful if you think that you can classify a lot of data in a very fast way, even though it's a sort of, how can I say, statistical view on this. And even though, unfortunately, this is not fully explainable AI, the field of explainable AI is growing. It would be nice to understand what kind of semantics lie behind the features you saw. So all those numbers defining your vector. But in any case, this system is good enough to obtain results which are not 100% accurate, but maybe 98% accurate, which is not bad at all. So that was it. I can stay here for questions if you have any, or in any case, if you don't have time, I think we ran out of time. So I'm available, but you're also free to go if you cannot stay because you have other things to do. But otherwise, for whoever is curious or wants to know a bit more or didn't get something, I'm available. So I asked the TA at least to say something to help me see whether there are other questions or other issues.
Teacher, maybe there are no other questions.
Okay, anything else that you might consider to be useful or necessary, or because if there are no questions and everything is hopefully clear, then we can soon close the class. Okay, then was a pleasure. I would say seeing you, but I didn't see you meeting you. Oh, there is a question. Please. I see many other questions, so let's start. I cannot really read the, first the first person. TT. Let's see in chat, maybe they wrote in chat. Thank you. Thank you for thanking me. Thank you. Yeah, sorry, it was a lot of stuff. Someone says I need to watch the video again. Yes, I think I mean, it's not something easy. In 1 hour and a half, I did something that is probably requires some days of work, but I hope I provided you with a comprehensive workflow. Even though it's very basic, it could be useful, I think. But the question, I cannot actually read your name, Thimideutran, not sure, TT. I asked the TA to please, tell me if there are questions I cannot interpret because I cannot pronounce some of the names. TA, please help me.
Hey teacher, I'm here. You want me to close our lecture or?
No, I see that someone is sometimes raising the hand, and I don't understand whether there are questions or not. But I don't know how to pronounce some names, and I don't know what to do. But if you think that there are not really questions, just kind of comments like thank you, then it's okay for me. And in that case, I will close the.
Yeah,
I will
teacher,
close.
maybe they just want to express their gratitude because this image might just a representative of their emotion, not they show their hands up.
Okay, perfect. Then thank you so much, and I'm in any case reachable. You know my data, and so that's it. I hope you enjoyed this lecture, and I hope it was maybe a bit different from usual, but useful as well. And best luck with your studies, and I hope to see you maybe in China, maybe in Italy, and maybe conduct some kind of interesting research in the future. Thank you very much. And thank you very much, you TA. Goodbye. The recording, can you please then send me as well? It would be nice to have also for me.
Okay.
Okay, thank you. Is it a question, TC?